Hello everyone and welcome to Instant Biology by Dr. Neela. I am here again with another exciting video that is basically a part of Numerical Knockout series. And in the last video of Numerical Knockout, I had discussed some important bioprocess engineering questions with all of you. Now, many of you appreciated the bioprocess engineering part of the Numerical Knockout series and had requested me to take more videos on bioprocess engineering since gate examinations are fast approaching. Now you would be knowing that bioprocess engineering is a very important and integral part of gate biotechnology examinations, and it comes for approximately 27 to 30 marks in each year. So in today's lecture, I would again be taking some questions from the bioprocess engineering part, unit number 4, unit number 5 of GATE biotechnology syllabus. I would be showing you how you can do questions using the simple formulas, using some important tricks, and I would definitely suggest you to watch this video before the examinations, because in this video I am taking numericals from different portions of your GATE biotechnology bioprocess engineering section. So without wasting much time, let us start the numerical knockout session, bioprocess engineering related PYQs, part number 2. I have already made a video that is named as part number 1. You can go to my numerical knockout session playlist and you can search over there. So the last video was on bioprocess engineering only. So let us start today's video. So I'm just showing you the first question on your screen. So the equilibrium potential, you can see the question. You can see that the equilibrium potential of a biological membrane for Na plus, let me just quickly mark the important sections over here so that we can focus upon those things only. So the equilibrium potential of biological membrane for sodium Na plus is 55 millivolt at 37 degrees centigrade. So what you can see over here is that the sodium, the ion that is given is sodium. So the ion that we are talking about over here is sodium, Na plus ion, and the equilibrium potential, equilibrium potential that is denoted for the sodium ion is 55 millivolt. So let me just write it down over here, just give me a minute. So it is given as 55 millivolt. Now obviously you know that millivolt cannot be used, it has to be converted into the volt. So if I convert this 55 millivolt into volt, it would be 55 into 10 to the power minus 3 volt. I would be doing the subsequent steps. 55 millivolt, and the temperature that is given over here is 37 degrees centigrade. So the temperature is equals to 37 degrees centigrade. Now you would be knowing that the temperature cannot be directly taken in degree centigrade, it has to be converted in degree Kelvin. So in order to convert degree centigrade into degree Kelvin, what you have to do is you just add 37 plus 273. Whatever temperature has been given to you in degree centigrade, you can add 273 degrees and it would be converted into degree Kelvin. So if you add this up, it would be coming out to be 310 degree Kelvin. So this would be the temperature. Now let us move on. Concentration of sodium inside the cell is 20 millimoles. So sodium Na plus inside concentration has been given to us as 20 millimole. Now you would again be knowing that we cannot use millimoles into the formula, and therefore it has to be converted into moles. So 20 into 10 to the power minus 3 moles. Okay, assuming the membrane is permeable to sodium ions only. Now let me draw a cell so that I can explain it to you that how or what I am talking about. So let us say that this is a cell. Okay, I'm not drawing the double membrane structure over here because I want to explain something else, and I'm not focusing upon the cell biology over here. I'm focusing upon something else. Now you would be knowing that sodium potassium pumps are present on the cell membrane. Now what is the function of sodium potassium pumps? The function is that they will be sending out sodium ions, and they would be bringing in potassium ions. Okay, this is the function. Now they are saying that as of now, or in this particular question, you have to only consider that sodium ions are moving, or the membrane is permeable to sodium ions only. You do not have to consider potassium ions over here. In general, or in the past GATE biotechnology examination, questions have not been asked simultaneously on two ions, so they would be focusing upon one ion only. So two times sodium ions has been asked and one time potassium ion also has been asked. I would be showing you how you can calculate the potential, or what is the formula for the potential, or how you can calculate it. So in this particular question, assuming the membrane is permeable to sodium plus ions only, that means we do not have to consider the potassium ions. The sodium ion concentration outside the membrane will be, what would be the concentration of sodium ions outside the membrane? So sodium plus outside, we are not aware about this, and let us consider this as X. Now, so we know all these things, and apart from that, Faraday constant has also been given to us. Faraday constant, that this is equal to 23062 calorie volt mole inverse. Now many students ask me that do we have to remember these values, or they are always given in the question? No, they are not always given in the question. It is better to remember the important values, for example the value for R, or for example the value for Faraday constant. So gas constant also has been given to you, and the value for gas constant is 1.98 calorie per mole per Kelvin. So these are the values that have been given to you. My suggestion would be, when you are solving the bioprocess engineering questions, you should be writing down whatever has been given to you. This would allow you to think more carefully about the formula that can be used. Now, for those of you who know little bit of bioprocess engineering, they would recognize that what question or what formula can be used in this question, because this question can be solved by Nernst equation. You might be knowing about this. If you do not know, let me just write it down over here. And this is an important equation, Nernst equation. Now Nernst equation is used for calculating the potential, basically equilibrium potential because of certain ions. Now what is the formula that I would be using over here? Let me just write down the formula. So E equilibrium due to sodium ions, this will be equal to RT upon NF into natural log Na plus out upon Na plus in. So R means, let me just explain what are the values over here. Please practice this particular type of questions because they have been asked thrice in the GATE biotechnology examinations. Previous year questions, they have been asked thrice. R is your gas constant, T is your temperature in Kelvin, N is your the charge basically, and F is your Faraday constant, natural log ln Na plus out upon Na plus in. This is the formula. Now let me just quickly solve it. So equilibrium of sodium ions has been given to you. Let me just quickly write it down. It was 55 into 10 to the power minus 3. This value is equals to R. The value for R was also given. It was let me just check it out. It was 1.98. And the value for temperature I had already written. It was equal to 310 degree Kelvin divided by NF. Now the charge basically on the sodium ions is 1. There is no doubt about that. So 1 into Faraday constant, the value for Faraday is 23062 natural log, and I have already mentioned that I would be using X in place of Na plus out divided by Na plus in. So the concentration of Na plus in was given as 20 millimolar, which can be written as 20 into 10 to the power minus 3 molar. Right, now let me just quickly solve it. So if I just solve it, 55 into 10 to the power minus 3 into 23062 upon 1.98 into 310 is equals to, if I want to convert natural log into the log base 10, I can multiply it by 2.303. So what that is the same thing that I'm doing. So 2.303 natural log can be converted into log base 10 x upon 20 into 10 to the power minus 3. Now this is what we get. What we can do further is, if I solve this, whatever is on the LHS, if I solve this, it would be coming out to be 2.066. This is what I had calculated, and then you can bring down 2.303 over here just like this. It will be equal to log x upon 20 into 10 to the power minus 3. Now I'll just add up one page like this. So now obviously 2.066 upon 2.303, it will be equal to 0.897. So let me just write it down. 0.897 is equals to log x upon 20 into 10 to the power log x upon 20 into 10 to the power minus 3. Now definitely I'll have to take anti-log of 0.897, anti-log of 0.897. This will be equal to x upon 20 into 10 to the power minus 3. Now anti-log of 0.897, if you take, you will be getting 7.888601. This will be equal to x upon 20 into 10 to the power minus 3. And if you solve this, x value would be coming out to be 157.76 millimolar. So this is the answer basically, and this is the formula that you would be using. The same formula can be used, for potassium also. Sodium out upon sodium in has been used over here. Remember, Nernst equation is an important equation. That is why I have solved a question over here of the Nernst equation. We have done nothing fancy. It was just, we just converted the SI, we just converted the units into the usable units. You cannot use millimoles, and you have to convert it into moles. Similarly, you cannot use millivolts, you have to convert it into volts. And then finally you have to use the formula directly, that is the Nernst equation formula, and then you just have to solve it. So this is the value, 157.76 millimoles is the formula that you are getting over here. So yeah, so it was 20 millimolar that we obtained over here. That was the concentration inside, and outside concentration is 157.76 millimoles. Now let us move on to the next question. A bacterium produces acetic acid from ethanol as per the following reaction. Now they have given you a reaction, as you can see, 2CH3CH2OH plus 2O2 gives off CH3COOH plus 2H2O. The thermodynamic maximum yield of acetic acid from ethanol in gram per gram. Now, so this is a very common equation and most of you would be knowing this. And the question that they have asked is thermodynamic maximum yield of acetic acid from ethanol. Now, this is, you would be knowing that this is ethanol and this is your acetic acid. Now, when do you think that a maximum yield would be formed? Maximum yield is achieved when there is no increase in the substrate, there is no increase in the biomass concentration. Then only you would be getting the maximum product yield. Now, let me just quickly solve it. First of all, how can you get the maximum product yield, or how you would be obtaining the maximum yield of acetic acid? Of course, we have to first of all find out the value for F max. Now what do you mean by F max? F is the stoichiometric constant of your the product that we are using. So why are we using max value over here? Because that is what is being asked to us. That means we have to calculate the thermodynamic maximum yield. That is why we have to understand, or we have to find out the F max value, that is the maximum, that is the thermodynamic, that is the coefficient stoichiometric coefficient of your product, maximum stoichiometric coefficient that can be achieved. So we have to calculate the F max first. Now, in order to calculate the F max, what is the formula? Formula for calculating F max is equals to W into gamma S upon J into gamma P. So this is the formula. What do you mean by this omega value or W value, whatever you can call it? The value that is present over here, it is resembling, or it is giving us the number of carbon atoms, number of carbon atoms in the substrate, and J is giving you number of carbon atoms in product, and this gamma value is giving you the degree of reduction of substrate, and gamma P is giving you degree of reduction of product. That means we have to find out number of things. We have to find out, firstly, our aim should be, and of course after calculating the F max value, we have to use another formula by which we would be getting the thermodynamic maximum yield. So first of all, let us go step by step and first of all calculate the F max value. Before that, let me just find out what is the molecular weight for ethanol also, and what is the molecular weight of acetic acid also, and then we would be calculating the available electrons, and then we would be using the formulas for getting to the desired results. There are multiple steps to this particular problem. Let us first of all find out what is the molecular weight for the ethanol, that is the substrate over here. Molecular weight of ethanol. So how can we calculate the molecular weight of the ethanol? That is CH3 CH2 OH. This is given to us. So obviously 12 plus 3 plus 12 plus 2 plus 16 plus 1, this is what we are getting. So if you calculate this, so 12, 13, 14, 15, 12 plus 12, 24, 25, 26, 27, 28, 29, 30, and this would be coming out to be 46. This is the molecular weight for ethanol. Now, if I want to calculate the molecular weight for acetic acid, because I would want that also, so let me just quickly move on to the next page. Molecular weight of acetic acid. Now CH3, this is the formula for acetic acid, CH3COOH. Now let us calculate this. So 12 plus 3 plus 12 plus 32, because there are two oxygens, plus 1. So 12 plus 12, 24, 25, 26, 27, 28, 28 plus 32 would be 60. So this would be the molecular weight for acetic acid. Now we have achieved the molecular weight, but we also have to find out the degree of reduction. Let us calculate the degree of reduction for the substrate. Degree of reduction of substrate. And what is your substrate? It is basically ethanol. So I'm writing it as gamma S. And what is the degree of reduction? It is equal to the available electrons divided by number of carbons. Now what is the available electrons in case of the ethanol? If I calculate the available electrons, it would be, let me just quickly calculate it over here only. So available electrons, I just have to calculate the valency. So carbon is having 4. So let me just write it down. 4 plus 3 plus 4 plus 2 minus 2 plus 1. This is how the available electrons can be calculated. Carbon has 4 valency, So therefore I write 4, hydrogen as 1 each, so it will be 3, again carbon as 4, again there are 2 hydrogens, so 2 I'll write, oxygen is -2, so I've written -2, and hydrogen again has 1, so I've written +1. So this is the way in which I can calculate the available electrons. So 4 plus 3, 7, 8, 9, 10, 11, 12, 8, 9, 4, 3, 7, 8, 9, 10, 11, and this can be cancelled out, and this will be equal to 12. That means the available electrons in this case is 12, and yeah, so total available electrons are 12. The number of carbon atoms, of course, is 2 in case of the substrate, that is ethanol, so it will be coming out to be 6. That means gamma S is equals to 6. Now the same procedure we have to repeat for the product or acetic acid. So degree of reduction for, let me first of all calculate the available electrons over here. Available electrons. So available electrons can be, again carbon has 4 plus 3 plus 4 minus 4 plus 1. So -4 why I have kept, because there are 2 oxygens and each would be having -2. So +4 -4 has been cancelled out. 4 plus 3 7 plus 1 8. This would be the available electrons, and degree of reduction can be calculated as degree of reduction of product. This can be given as gamma P. It can be calculated as available electrons upon number of carbons. So it would be 8 upon 2, and this would be coming out to be 4. So this is one value, this is another value. Now what we have done is we have achieved what we required in order to calculate the F max value. Now let me just put in all the values for calculating the F max. First of all, I'll have to add up one page also. So what was the formula for F max? Let me come back to the F max formula. F max is equals to into gamma S upon J into gamma P. So what is the number of carbons? Basically I have already written that this is number of carbon atoms in the substrate mega. W is the number of carbon atoms in the substrate. J is the number of carbon atoms in the product. Okay, so you can give notations. I mean, there are different books, and in different books there are different notations that are given. For me, W is the number of carbon atoms in the substrate, and J is the number of carbon atoms in the product. So that is what I am using. In the substrate, the number of carbon atoms is 2, and in the product also the number of carbon atoms is 2. So what I'm going to do is that, yes, so 2 into gamma S, I calculated gamma S value, it was 6. 2 into 6 divided by the value for J, the product, into the, again the degree of reduction for the product or the acetic acid is 4. So this would be equal to 6 upon 4. This would be the value for F max. So F max would be this, or you can just quickly calculate it. So this would be 3 by 2 or 1.5 moles. This is the maximum stoichiometric value that you would be getting for the product. Now this does not end our question, because we have to find out the maximum thermodynamic yield, and for obtaining maximum thermodynamic yield, this was a small step. Now coming to the final formula for the maximum thermodynamic yield. So maximum thermodynamic yield, it would be, or it can be calculated as F max into molecular weight of product upon molecular weight of substrate. So this is what we can do. So I have already calculated the molecular weight of the product and substrate in the initial portion of the question only. So there is absolutely nothing left to do now. F max we have already calculated, it was 1.5. Molecular weight of product, if we calculate, if we just go back to the molecular weight of the product, it was 60, and molecular weight of substrate, it was 46. So it was 60 and 46. So 1.5 into 60 upon 46, and this would be coming out to be 1.95 gram per gram. So this is what we would be achieving, 1.95 gram per gram, because they are asking in gram per gram only. So this is what we would be achieving. So this is how the second question can be done. Again, the stoichiometric questions are asked a lot, so you have to because I took this question primarily because there are multiple concepts in this question. I told you how you can calculate the available electrons, I told you how you can calculate the degree of reduction, and then I told you how to calculate the maximum thermodynamic yield and Fmax value. So all of these things it was required to calculate all those things in this type of a question. That is why I had chosen it. So in one question I have told you multiple concepts. Now let us go back to another question. This is a question that is related to scaling up. If you remember my last video in which I was the bioprocess engineering part 1 video, then you would remember that in that video also I had taken one scaling up question, because scaling up is such important topic, and you cannot leave that. Almost in all the examinations questions related to scaling up have been asked. Now let me just quickly tell you this. The diameter of a large and a small vessel. So large vessel diameter, let me just quickly write it down over here. So large vessel dia has been given to us, and it is 1.62 meters, and then the small vessel dia has also been given to us. Small vessel dia is equal to 16.2 centimeters. Now again you can see a variation in the unit that has been given over here. So I can just quickly convert the meter into centimeter, because that would be more appropriate for us, because again we would not want to deal in decimals and everything, so we would not want to make our calculations such complicated. So what I can do is I can just convert it into centimeters, and this would be 162 centimeters. I've just multiplied it by 100 so that I can convert meter into centimeter. Now this would be, as it is, 16.2 centimeters. The vessels are geometrically similar and operated under similar volumetric agitated power input. That means P by V value is constant, because they are saying that the vessels are operated under similar volumetric agitated power input. That means P by V ratio should be constant. However, we are more inclined towards calculating mixing time, and mixing time in the small vessel was found to be 15 seconds. So let me just write it down. Small t I am using to denote the mixing time, and small t like this, and then I can just write it down, TTS. That means the mixing time of the smaller vessel can be given as TS. Okay, so TTS has been I have written it as 15 seconds. Okay, now I have to calculate the value for T large vessel, and this is, let me consider it as X. Now remember, basically you can calculate it in a number of steps also by, you can calculate it by the formula in which the frequency and the diameter are correlated, and then you can move on to the mixing time. But I will be giving you a formula through which you can directly calculate the mixing time if P by V ratio has been given to you as constant. How you can calculate it? There is a simple formula in which the mixing time, or let me just write it down, T1, let me just not write it down as TS and TL. Small t capital T1 upon small t capital T2 is equals to, and this formula is directly correlating to the diameter of the vessels. So that is what has been given to us in this question. So we do not need to move on to the impeller frequency. We can directly calculate it by the diameter formula. So this is the formula is dA2 upon dA1. So it is just inverse. That means the mixing time of the vessel number 1 upon vessel number 2 is equal to the diameter of the vessel number 2 upon vessel number 1 to the power of 11 by 18. So see, this is a direct trick that you can use in your questions. If P by V ratio has been given to you as constant, and then you have to find out the mixing time, and this formula basically is correlating to diameter. In this present question we are just given the diameters only, so it becomes extremely easy for us to calculate this kind of question. So now so now we can simply use this formula. Let me keep the dA2, let me just larger vessel diameter, so this is dA2, and smaller vessel let me consider as dA1. This will make things easier for us. And in that scenario, so the smaller vessel, larger vessel diameter is dA2, therefore the smaller vessel time can be written as T1 and the larger vessel time can be written as T2. So now let me put these things into the perspective, into the formula. So what we can get is, so yeah, so okay, I'm just writing down over here. So TT1 upon TT2 is equals to dA2 upon dA1 was the formula. So dA diameter A2 162 upon 16.2, it will be 162 upon 16.2, and this can be raised to the power of 11 by 18. Okay, yes. So now what we can do over here is that the T2, okay, I'm just this is just, I wrote it by mistake, I wrote it wrong. TT2 upon TT1, this should be the correct formula. That means we are directly correlating T2 upon T1. That means both the 2's will be in the numerators and in the denominators it will be both the 1's. That means, in other words, I can just write it down that the mixing time of the larger vessel upon mixing time of the smaller vessel is equals to diameter of the larger vessel upon diameter of the smaller vessel. So 2 is denoting larger and 1 is denoting smaller. This is what I want to say. Do not get confused. I just by mistake wrote 1 over here in the numerator. So this is what we are getting. So this would also be 2. So now let me quickly solve this. So TT2 we do not know. Let me consider it as x upon 15, because 15 seconds was already given. So 162 upon 16.2, you can quickly solve it, and this would be 10. So 10 to the power of 11 upon 18. Now you can solve this 11 by 18. What would be the value for 11 by 18? It would be 0.61. So I can write it down like x by 15 is equals to 10 to the power of 0.61. And 10 to the power of 0.61, you would be getting calculator, so that is not a problem. 10 to the power of 0.61 can be calculated as 4.07. So if you multiply it by 15, because we have to calculate the value for x over here, so 15 into 4.07, it will be coming out to be roughly as 61 seconds, because this is the mixing time that we have to calculate. So this would be 61 seconds, and the correct option is C. So I believe you would have got a clear understanding of this question also. Now, before moving on to the next question, I have a very important announcement for all of you. You would be knowing that every year we start our GAT-B batches around this time only. So this year also we are starting our GAT-B batches from the 28th of February. So those of you who are looking forward to giving the GAT-B examination after the GATE examination, you are most welcome to join the GAT-B sessions. There would be two free demo classes also, and they will be the first and the second demo class. And there are many important or many advantageous features of this GAT-B course. The course would be in bilingual fashion, plus we would be finishing off the material in 1 month. Apart from that, we would also be focusing upon the revision. In the revision, we would be solving MCQs from the previous year examination. You would be getting the notes for your lifetime, and the recordings would be available till the GAT-B examination. Apart from that, test series and everything is also included in this. The price for this particular course is 3,500 rupees only. So the related video would be, you would be getting the related video over here at the top, and you can, if you wish, you can join, you can connect with us on this particular number. So I'm just writing the number over here. If you want, you can always connect with us. 8299134528. This is the WhatsApp number. Okay, and you can connect with us. Apart from that, the email ID has also been given in the description section. You can just connect with us through the email also, but this would be a more preferable method and a more direct method. Now let us move on to the next question, and the next question is basically on the chemostat. A chemostat is operated at a dilution rate of 0.6 per hour at steady state. At steady state, the biomass concentration in the exit stream was found to be 30 gram per liter. The biomass productivity in gram per liter after 3 hours of steady state operation will be. Now this is a extremely simple question, I must say. It is just checking your concept, because they are giving 3 hours over here, so they are just testing whether you are able to understand the concept of 3 hours that they are given over here or not. Let me just quickly explain it to you. The dilution rate has been given over here. Dilution rate has been given as 0.6 per hour, and the biomass concentration in the exit stream, the biomass concentration, that means X, has been given to you as 30 gram per liter. Now the biomass productivity, now you should be knowing the productivity has a very simple formula. Productivity you should be knowing, because a lot of times the questions on productivity are asked. Simply always remember, productivity would be X into D. This is the productivity. Okay, of course this is per liter and per hour. This would be this productivity would be per liter per hour. Now if they are asking you for the entire volume, you will have to multiply it by volume also, but in this thing, the biomass productivity in gram per liter per hour after 3 hours of steady state operation will be. You should be knowing that the productivity is always given in per hour. Working for 3 hours does not or would not create any impact on the value that you would be getting for the productivity, because it is again calculated per hour and per liter. Okay, so that is why this 3 hours is just creating a confusion inside your mind. You can just directly multiply the X into D. So what we are having is 0.6 is the dilution rate multiplied by 30 gram per liter, and this would be coming out to be 18 gram per liter per hour. So this is the value. Of course you can see this is gram per liter, and this you multiplying by per hour, so you would be getting gram per liter per hour, and this would be the answer, 18 gram per liter. Remember this, these little concepts are extremely important, because the questions that are asked are not actually very tough. The problem is that we do not understand the concept only. Now coming to another question. In this question you can see that the decimal reduction time of the bacterial strain has been given to you as 20 minutes. Now remember that in the previous bioprocess engineering session that I had organized, in that also I had told you that decimal reduction time questions are asked a lot. Okay, so you should pay special attention to these questions and practice them a lot. So now specific death rate constant in per minute. So specific death rate constant, basically this is KD value that they are asking you, or the rate constant. Now simply the formula is very simple for decimal reduction time. Decimal reduction time has been given to you over here as 20 minutes. Okay, now remember that the formula for decimal reduction time, or D value, let me consider that D value. So D value is considered as 2.303 upon K. Now this is KD value, or the specific death rate constant that is given over a KD. So how can you calculate the K value over here? Just K is equals to 2.303 divided by 20. So this would be actually coming out to be 0.115. This would be my answer. So this is extremely easy. Now the only thing that you should be knowing is decimal reduction time is connected to your KD value or the specific death rate constant by this particular formula. You should be knowing this formula. Okay, so these were the questions that I think are very important with respect to GATE Biotechnology 2025. You should pay special attention to these and practice more of these. I hope you understood these topic and you would have enjoyed studying. And you can comment in the comment section about how you liked this video. Apart from that, also tell me which topics you would want to take more would want me to take more questions on. Thank you so much. All the best for your GATE Biotechnology examination. Have a good day.